take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes.
Welcome to Life in Red.
So I am the type of person who, when science class came around, I always tried to skip and go play on the sports teams because math was always really hard for me. I'm so excited to be joined by Heloise Stevance. How are you, first of all?
Hello, Ryan. Thanks so much for having me. I'm great. I'm really good. How are you?
I'm very well, thank you. It's some beautiful weather here in Ottawa. You're in New Zealand, so you're also my first guest who's out of the country. So
wow. And quite far as well.
Yeah, literally where I'm recording right now, it's 6, and we had to figure out you're at 10 a.m. So you're having your morning coffee.
Yes,
I'm
exactly.
My evening beer.
Nice. I could have my morning beer.
Oh yeah, I guess that works too, eh? It's 12 o'clock somewhere, as they say. I'm so excited for you to join me because you are an astrophysicist.
I am.
And to me, I think that is literally one of the coolest jobs you could ever have in the world, because space is just one of those things that is so exciting and cool, yet most people like myself don't know enough about it.
I love my job, so I can't disagree with you. I'm going to say that.
It's like, oh yeah, we've been to the moon, and we have black holes and like that. That's kind of like asteroids, and that's pretty much the extent of our knowledge. So I first off want to ask you, how did you fall into becoming one of these? Because I can't imagine that's an easy road to go down.
Well, that's an interesting question because I kind of fell into it to some extent. So I'm actually French, and when it came to deciding what I wanted to do after high school, I decided that I wanted to go to university, and I decided that I wanted to go to the UK for university because the university system is a little bit different in France and in the UK. And so when I was looking at different places that I could go and what kind of courses that I could do, I realized that I could actually pick an astrophysics course, and not just like a single course in one semester, like an entire degree in astrophysics. I didn't know that was possible until I was 17. And when I saw that, I was like, oh my God, I was always interested in space when I was a kid. I always watched these documentaries. I read those books. I didn't realize that was something I could do. And I nearly didn't do it because physics scared me. So I was okay at it, but the math scared me and I thought I was bad at it. And one of my older cousins, much older, he's a half cousin. He was 40. He was like, don't limit yourself. Do not put limits on yourself. If you want to do it, you do it. You see where it goes. If it doesn't go anywhere, that's fine. You've tried it, but do not limit yourself. And so I actually signed up for the course. And then I got my master's. And then I started my PhD. And I never stopped loving it. And that's how I got here.
Really? So what, do you work at a university now? Is that kind of the job? Are you a teacher, professor? Or are you just kind of doing straight research?
Right. So right now I'm doing straight research. I'm what we call a postdoc. So when you do astronomy, when you finished your master's, to go into research, proper research, you need to do a PhD, a doctorate. And once you finish your doctorate, you can't really get a permanent job straight away. You need to do a few postdoctoral positions. And that's where I'm at now. I finished my PhD a year ago. And the postdoctoral position I'm in is 100% research. Mm-hmm. Now, that doesn't mean I don't really teach. It means I don't really teach undergraduates, but I co-supervise students, but they are research students. So their output will be research. It's just that I help them along the way and we work together to get those results.
So one of the questions I always like to tackle when I'm having a guest on is, when you think of astrophysicists, Neil deGrasse Tyson comes to mind, Carl Sagan, Brian May from Queen. There's not a lot of women that are kind of out there. So how was the journey hard to get where you're at, being, a woman and trying to get in that field? Was there a lot of women in your class? I'm just trying to get a sense of like the diversity in the field.
Yeah, so it is true that we struggle with diversity in general. So women in STEM is a problem, but we also have a strong lack of people of color. That's really problematic as well. So yeah, the physicist in your mind is a straight white man.
Yeah.
And that's kind of where it is. So it is a struggle to some extent. I struggled with my gender expression when I was an undergraduate. I was very manly. I was not that my gender expression goes from one end of the spectrum to the other, but I didn't feel comfortable expressing my femininity when I was an undergraduate. And that's just a very personal thing. But there's also a lot of things that you start to realize when you get on with your research and you really get into the job and you see that you're being treated differently sometimes. So if you're very assertive as a woman, you'll be called aggressive. If you're not assertive enough, you'll be talked over. And in a way, there's no way to win. If you are faced with that with the classic status quo, you can't win. If you're if you're too gentle, you get fucked. If you're not if you're trying to assert yourself, then you get called that bitch, or you are too aggressive.
Right.
And so the only way to actually move forward is to make people aware of all of these unconscious biases that we have, that these stereotypes about certain genders, about different ethnicities, about different cultures, and how we react to that. And I was quite fortunate to know pretty much as many people who were aware of these things as people who were problematic. And that's what helped me get to where I am today, because, I nearly left the field, but I didn't, because I got that support, and it's invaluable. And we really need to get more allies, more men, to understand how this system oppresses minorities and how they can help just by being aware, just by seeing what we see and speaking up sometimes on our behalf, because if it comes out of their mouth, it will be taken more seriously sometimes.
Yeah, because you get that sense a lot with business. And I think outside of academia, there's that conversation isn't necessarily had the same as, gender roles in business. So that's what I was kind of wondering, like, if, I always imagine like it's hard to be taken seriously as a woman, especially in this field, right? Like, it's just that would be just a base perception that
and it's not just being a woman, it's also sometimes being feminine. So if you're a woman but you're kind of abiding by all of these codes, these very stereotypical manly things, then you can be taken more seriously than if you're typically feminine,
right?
Because these things are seen as illogical or not clever or vain or whatever, unfairly, really. And but I try to not let that stop me, especially when I do outreach. I kind of make a point to like wear my nice dress, put on my makeup, and do all of that stuff, because I want to show a different image of what science is, and show that you can still enjoy all of these things that are not stereotypically what you expect from a scientist, because we are multifaceted individuals.
Yeah, I picture Pete, the boring, that white guy in like the boring brown suit, just wacky hair. So I appreciate like someone like yourself coming on and being excited and like getting ready to tell everybody about all this wonderful space stuff, instead of just like Ben Weinstein being like, oh, like in the lecture class. You're like, oh my God.
Bless him. Yeah. But see, that's something as well that we need to take into account. It's because for a long time, the narrative was, how do we change women? How do we make women act more like men so that they can fit in? But we need to take a step back and look and see and ask ourselves, are these behaviors really what we should want from our scientists? Are people who are not really sociable, like the classic kind of stereotype, the scientists that can't talk to people, that are a bit abrasive, that don't have as much empathy, that are a bit selfish? Like, is this really what we want from our scientists? Or do we want them to have that empathy for people that don't necessarily understand the science or don't understand it yet? Do we want our scientists to be better communicators, to be better at working in teams, to not be so individualistic? maybe we can change what we expect of scientists rather than changing what we expect of women in science.
Absolutely. So you said you're doing research full time.
Yes.
What are you researching specifically? And feel free to get into as much detail as you want, because I just want to have my mind explode.
Okay, feel free to ask as many questions as you want.
Yes, please.
Okay, so at the moment, I'm working on what we call stellar populations. So it's just a bunch of stars and understanding how they evolve and how they live their life and how they die. And that's how we understand the stars in our universe, really. And the goal of my particular project, ultimately, is to understand where gravitational waves come from and where kilonovae come from. So are you familiar with gravitational waves a little bit? Should I explain that?
Yes, because I want to say yes, but then I feel like I'm not.
Okay, so
I know gravity, if I'm thinking of gravity, am I along the lines there?
Yes, absolutely.
Okay.
So gravitational waves are freaking awesome. Gravity is really a really special force, and we need to think about the fabric of space-time when we talk about gravitational waves. So every object that has a mass in the universe distorts the fabric of space-time a little bit. Kind of imagine a bed sheet that's pulled like really, really tense between two poles, like flat. And if you put a metal ball in the middle, it will create a little dip, right? Can you picture that? Mm-hmm. And if you put a metal ball that's heavier and denser, it will create a bigger dip, and it will create a bigger well. Well, the fabric of space-time is the same, but in 3 dimensions. And that's how you end up rotating around stars, is because they create that kind of well that things fall into and rotate around. That's how the Earth rotates around the sun. That's how the moon rotates around the Earth. But if you get objects that are really, really big and really, really dense, like neutron stars, then that well is really, really, really intense and really deep. And if you have 2 neutron stars rotating around each other, then they're going to, that warp in the fabric of space-time is going to rotate as well, right? And you're going to create waves. Just, imagine you're throwing a rock into a pond and you get these waves kind of spreading away from the impact. That's the same idea. You get these waves in the fabric of space-time. Well, these gravitational waves can be detected now. Since 2015, we have the power to detect these waves in the fabric of space-time. And so if you want to know more, you can Google the LIGO and the Virgo collaboration. They do incredible work. They can detect motions in space of the order of 10 to the minus 21 meters, which is a one with 21 zeros in front of it, which is really insane. Like the size, it's 1,000 times smaller than the nucleus of an atom.
Okay, that's really small.
It's insane. Like I don't even understand really how you can measure that kind of length. Like how can you measure something that is 1,000 times smaller than the length of an atom? They are incredible physicists. Anyway, so we can detect these gravitational waves. And like I said, you can get these gravitational waves if you have 2 very heavy masses in space rotating around each other, right? And so my job is to understand how you get these 2 masses rotating around each other and then eventually merging, because when they merge, they create a giant explosion that we call a kilonova. When you get 2 neutron stars merging, you get an intense burst of light. And in that burst of light, you also create new elements. So you create gold, you create platinum, you create rare earth elements, and all of these things that we actually have on Earth. They need to come from somewhere. They didn't come from the Big Bang, because the Big Bang only created hydrogen, helium, and trace elements, right? So these things need to come from somewhere. And so these kilonovae is something that we've been studying over the past few years. And my job is to help my boss understand where they come from, because she's got this really amazing simulation. So she can simulate 1 million solar masses in in a computer. So you take the equivalent of 1,000,000 times the mass of the sun, and you divide it up into a bunch of stars, right? Like a mini universe in a computer. And then you make them evolve all together for like millions and millions of years, quote unquote. And then you see what they do. You see how they evolve. You see how they get together. You see if they merge. You see how they create gravitational waves and all of that stuff. And then you can compare it to our real universe and the real observations that we see from telescopes and from space telescopes. And if it matches, then that means you've understood how the universe works. Right. But getting to that point is quite the puzzle.
So the sun in our
Yes.
galaxy is a star.
Yes.
And it's quite big. See, that's my knowledge of space.
Yes.
When we're talking about these giant, what'd you call them again? Sorry.
The neutron stars?
Yeah, the neutron stars. How, like, in comparison to the sun, what are we talking about here?
Okay, so what's really crazy about the sun is that it's not actually that big for a star. I mean, it's a bit bigger than average, but the sun isn't that special. And neutron stars come from more massive stars. Neutron stars are actually dead stars, and they are the remnant of a much bigger star that lived its entire life and then died. So if you get a star that's more than 8 times the mass of the sun, at the very least, then it's categorized as a massive star. And these will have very different lives. They will live very quickly, so millions of years instead of billions of years. They will burn their fuel really quickly. And then they will die as a supernova. And what happens when they die is that basically they've burnt all of the fuel that they can. And when they run out of fuel, then gravity wins, basically, because stars are big balls of mass, right? And so gravity is constantly pushing everything in. And unless there is something to counteract that gravity, they would collapse, right? The thing that counteracts gravity is the fusion inside the star. So if fusion stops because you've run out of fuel, your core collapses. When the core of a massive star collapses, the pressure is so dense that the electrons, so the negatively charged particles, and the protons, the positively charged particles, have to merge into neutrons. And when they do, they can be even denser than any other star in the universe. And so what ends up happening is that 1.5 times to 2 times the mass of the sun is condensed into an object that's only 20 kilometers across. So the sun is in radius 100 times that of the Earth. So it's 100 times bigger than the Earth in radius. 20 kilometers is the size of a city. So you take all of that material and you condense it pretty much as you can. If you were to condense it further, it would have to be a black hole. It would no longer be a star, right? So it's as dense as it can get. It's the density of a nucleus. And that's why they have such incredible, what we call potential wells. So that's why they create such incredible divots in the fabric of space-time. That's why they warp them so much, is because of their density. It's how much mass you can fit into a tiny space that really creates that well.
Right.
So yeah, they're extreme.
Okay.
Absolutely extreme.
Now, I don't even know if we know the answer to this as a human race. Are all the stars in the universe, are they already created, or do new stars pop up all the time?
Pop up all the time. It's incredible. So, and you have different galaxies that do different things. Right. So we can classify them in star-forming galaxies and what we call quiescent galaxies. So they're just not doing much. Most of the star formation in the universe happened billions of years ago. I need to think about this in 10 billion years ago, something like that. It's just that it's not the scale that we usually think about. We talk about redshift. So if anyone out there understands what redshift is, it's at redshift 2. But so it's about 10 billion years ago that most of the stars in the universe were created. But we still have star formation ongoing. We have star formation ongoing in the Milky Way. And yeah, absolutely. The sun is like a 3rd generation star or something like that. So a bunch of stars were formed and died, and then their gas was given back to space, and then that gas condensed again into stars, and these stars died, and then the sun was born. And we know that because the sun is, it's made mostly of hydrogen and helium, like was created in the Big Bang, but there's like 2% of its elements that are heavier elements. They're stuff that has been processed by previous generations of star. There's no way these elements were created in the Big Bang. These come from previous stars that have lived their lives, done a great job of making new stuff, and then releasing it into the universe to make the stars that we have in our solar neighborhood.
It's funny when you talk about that. You're like when you're conceptualizing it in my head, at least, it's like, okay, like this one star lasted like 10 years and then went, and now the sun is like this thing that has such longevity. I assume that's not the case. I when you're thinking of the entire,
they last a long time. So there's kind of a limit to how long a star, like we think of it today, can last. So 3 million years is kind of the shortest lifetime. So the most massive stars live millions of years, and 3 million is about the shortest that they can manage. But 3 million years is nothing on the scale of the universe, if you think about it.
And that's what the thing that like just like blows my mind. Like you even think like the human history timeline, and then you put it with that 10 billion timeline, and then the universe. It's like you can't conceptualize it.
It's very difficult. It's very interesting because the way often how we think about these numbers, we can't think of it on the linear scale. So a linear scale is like 1, 2, 3, 4, 5, etc., etc. We usually think of it in powers of 10. So you're like 1, 10, 100, 1,000, 10,000, because there is no other way to cram all of these scales into your head and comprehend it as a human, because we do not deal with these scales very well. We evolve in, our little 3-dimensional world where we just walk 2 kilometers max, or like do our little run and everything. Mm-hmm. And so we can't conceptualize these numbers. So we have to think of it. And that's where some of the maths and the intuition, the mathematical intuition really helps you, so that you can think of all of these things. But yeah, it's crazy. And some of the stars in the universe, especially low mass stars don't last much, much longer than the high mass stars. Some of the lowest mass stars in the universe have lifetimes of trillions of years. They are much, much longer than the current age of the universe. And these stars are pretty much not going to do much in their life. They're just going to just live their lives very slowly, and then it's going to be the heat death of the universe, and they're going to have done nothing, because they're just so slow. And trillion is such a big number. It's very difficult to comprehend.
Do you or any other scientists ever have that kind of exponential dread when you're doing your work and you're thinking of these giant numbers and the infinite universe and all these different things? Like, does it ever like bring you down?
I think I used to when I was younger. But like when I used to think about it when I was like a teenager, because like I said, I was really interested in that kind of stuff. But now not so much, because I guess it just brings perspective to my life.
Right.
And like I'm insignificant in the grand scheme of the universe, but that doesn't bring me down. That, if anything, it makes me more optimistic and happy about my life, because the only thing that matters about my life is what I make of it and what other people in my life make of it. I'm not going to make a difference to the stars in the universe, that's for sure, but I can make a difference in the life of those around me and my community. And the only real meaning to my life is, how do I affect the people around me? And hopefully I will do that in a positive manner. That's the only thing that really counts in the grand scheme of things on the scale of the universe, because you're not affecting those stars. They're just living their lives. They've been living their lives. We will, as a race, die long before they will. And we're lucky to observe them, but we're not going to affect them in any way. And I don't know, I find that reassuring to some extent. It gives me more agency to what my life really means.
That's a good way to put it. Okay. How do you find these stars in the universe? Like, is there just some sort of like giant telescope that you can like look through
There's
and like you're just
several.
like, oh, look, a star.
Yes.
Oh, wow.
There's multiple, and also we're really terrible at naming things as a community. One of the telescope I've used a lot is the VLT, which stands for Very Large Telescope, because it's really big.
Amazing.
And there's one that we're trying to get built called the ELT, which is Extremely Large Telescope.
I appreciate that.
Yeah. So yeah, we do things like that. So yes, we have really big telescopes. We've got loads of telescopes. So the reason that we want to build big telescopes is because a telescope is basically like a bucket for light. The bigger the mirror, the more photons it gets, right? So if you went in the rain with a bigger bucket, you just get more water in. So the VLT, for example, is 8 meters in size, in diameter, which is as big as you can make a single mirror. What we call monolithic, so it's just one block of glass or ceramic rather. We are building bigger things though, and so the way that we do that is that we create segments. So we've got hexagonal segments, and then you just piece it together, and bam, you've got a bigger mirror. And so we're making things like that as well. But another really cool thing that we do is we send telescopes to space. So the Hubble Space Telescope is in orbit around the Earth. The James Webb Space Telescope is going to be not in orbit about the Earth, it's going to be in orbit around the Sun. So it's going to go to a bit further away. And these tend to be smaller in diameter because, you have to fit it in a rocket. It's really difficult to fit something that's 8 meters across in a rocket. But what's really good is they don't have to deal with the atmosphere. So that's something that some people don't think about. When it's not just about, observing at night and then you can see the sky as it is in space. It isn't, because the atmosphere is actually really bright. And it also creates a lot of perturbations. And we have to account for that. And it makes it harder to get like HD, basically. Putting a space telescope, putting a telescope in space is like getting an HD camera, because you can't get the resolution because the atmosphere just blurs everything. And there's also wavelengths, so colors, certain colors that you cannot get on Earth. So for example, the ultraviolet, the UV, is absorbed by the atmosphere very, very heavily, which is good for us because otherwise we would burn to a crisp every time the sun is out, so it's good for us. But it's really bad for UV astronomy because you just can't get that light. So that's why you have to put it in space. So the Hubble Space Telescope is really good at observing the ultraviolet. So all of those colors that are beyond blue.
Right. I would argue as a ginger, every time I do burn to a crisp.
Yes. So you're lucky that we've got that blanket, because otherwise you wouldn't survive 2 minutes.
So I'm curious about black holes, because those are kind of some of the things that I guess for people who have a semi-interest in space, it's always the thing that comes up.
Yes.
A couple of years ago, it might not even been a couple of years ago, it might have been last year, but we got a picture of it, like the first picture of a black hole.
Yes, it was last year. Yes,
it was last year. Okay, the 2020 has taken time out of.
I know, it's still March in my head. It's like.
Okay, what is a black hole exactly?
Okay, well, exactly, that's hard to say.
Oh, okay.
But no, okay. So you remember when I said that masses, like heavy masses and especially dense masses in space, warp the fabric of space-time, and it makes things kind of fall into their little divot and rotate around them. Mm-hmm. So the next step beyond the neutron star is the black hole. And so what happens there is that the little well that they create in the fabric of space-time is so deep that if you start falling into it, you can't come out, even if you're going at the speed of light, which is, the maximum speed in the universe. That means that photons, if they start falling into that well, will not come out. And that's why it's a black hole. That's why it's black. That's why it doesn't reflect or emit light. It's because it absorbs it all and doesn't let it come out.
Right.
So that limit of where things can't come out of the black hole is called the event horizon. And that's why the telescope that took the picture of that black hole is called the Event Horizon, it's called the Event Horizon Collaboration or something like that. That's where the name comes from. Now that doesn't mean you can't have things rotate around the black hole, because we do. So you can Google that actually. We've got videos of stars rotating around the black hole in the middle of the Milky Way. That's at the center of the Milky Way. So then it took like 10 years to get that video, and you can see stars shooting past in an elliptical orbit. But for that to happen, you need to be far enough away that you don't actually fall into the well, because if you do, there's no coming back. And so to get a black hole, you need something that's, you need a lot of mass compressed into a tiny, tiny space. So the radius of a black hole, given a certain mass, is called the Schwarzschild radius. I don't know if I'm saying that right, but there's a mathematical equation that you can calculate the radius of a black hole given a certain mass. So for example, if the Earth was a black hole, if you took all the mass of the Earth and wanted to make it a black hole, you would have to compress it to the size of a marble. That's the scale that we're talking about. So it has to be really, really dense, denser than any nucleus or atom that we know about. So what's in it? I don't know. Yeah. I'm sure physicists have their own ideas. I don't know whether it's quarks or a singularity, as they call it, or just a soup of elemental particles. Not sure. Because the thing is, you can't observe what's in the black hole. That's the thing. You can't observe what's in it because no light is coming out. No quote unquote information can come out of the black hole. Everything that gets into it is stuck, and you can't actually probe what's in it. Right. And so that's why they're so fascinating. And they come. So most black holes, like stellar mass black holes, that are like 3, 5, 10 solar masses, 30 solar masses. These come from stars, and the massive stars that I was talking about earlier. If you've got a really, really massive star, when its core collapses, it doesn't collapse to a neutron star, it collapses even further, it collapses to a black hole. And that's how you get these. Now, to get the very supermassive black holes that are like millions of solar masses in the center of galaxies, that's a very good question that astrophysicists are still asking themselves. And one hypothesis is that the first generation of stars, so that came just after the Big Bang, that was made of that primordial soup of elements, just hydrogen and helium. These stars were really, 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 really massive, like maybe 1,000, 10,000 times the mass of the sun. And these had very different lives and very different deaths, and could create black holes that were very massive and were the seeds of the supermassive black holes that we see today in the center of galaxies. But that's still a big area of research.
Right. As a person who, again, doesn't understand much about it, but you listen to I'm just going to call them like the stoners that are like, whoa, dude, like black holes. But is it possible, like, we're just sitting here having this podcast and all of a sudden like a black hole just like erupts and sucks in Earth? Like, is that like or like, can you like...
I can assure you that no astrophysicist is concerned by that.
Okay. All right,
we're more worried about climate change than we are about a black hole sucking up the Earth.
Okay, that's good to know then.
Because space is really empty. Like, to be honest, space is vast and it's mostly empty. So having a black hole that whizzes by, it will be way too far for anything.
Right. Okay. To get to like answer some of those like commonplace questions that a lot of people kind of ask and wonder about. So I don't know if you have the answer, but we'll just work through it. If not, it's fine. Travel to Mars. I mean, that's the one that people kind of always talk about.
Yeah.
In your opinion, as an astrophysicist, is that like a viable human, solution to problems on Earth, whatever, what have you?
I think that the people who claim that it is a solution to the problems we have on Earth, would like to think that there are no solutions to the problems we have on Earth so that they can get an excuse to go to Mars. So I'm not saying that going to Mars is a bad idea on the whole, but we shouldn't give up on our planet and fuck off to Mars. To be honest, it would be extremely difficult, if borderline impossible, to terraform Mars. I'm not saying it's impossible. If we didn't have a choice, maybe we'd find a solution. But it's just it would be so much easier to actually get corporations on Earth to do the right thing and fix their own issues than think about Mars as a second Earth, because it isn't on many levels. So, for example, Mars doesn't have a magnetic field, which is important. The Earth's magnetic field protects us from the sun and some of its outbursts of particles. And that's what keeps our atmosphere there and safe from the solar wind. We could create outposts on Mars, and that could be interesting in the future. But thinking about it as a second planet isn't a good idea. Right. It would be better to use these efforts to fix our shit down on Earth for the time being, and then look up again.
Yeah.
That's the problem with space exploration. Like, it's great, but if we think about it, the space exploration to the moon, the space race, was a pissing contest between the US and the Soviet Union. Mm-hmm. It was not driven by scientific inquiry primarily. Like, it did fantastic for scientific inquiry and for technology and for engineering, absolutely. But when it boils down to it, it was a pissing contest between two super forces that were trying to show which was the best. And I don't think this is how we should do science. I don't think this is what should drive us ultimately. Right.
So my next question then is, you get the random articles that pop up, whether it's New York Post or I don't even like Variety or these .org organizations, that will always come up with an article like scientists have found, another Earth or something that resembles Earth that may have life. Fact or fiction?
Okay. So I don't want to piss off the exoplanet people, but we're a little bit sick of their shit, to be honest. So here's the thing. So here's what happens. People find other planets that are similar to Earth. That is true. Like, they're similar in size. They might be similar in their location in their own solar system. So they're not too far out. They're not too close in. But the problem is that the quote unquote habitable zone doesn't mean that there is life on that planet. The habitable zone just means that there can be liquid water. So there are several problems. One, actually determining whether something in the habitable zone is dependent on certain errors that you can make with your measurements. And sometimes those are not well constrained. Like, it's within errors, but also like burning death is within errors. So it's like, okay, you pick that for the article kind of thing. But even if your measurements are all like super tight and everything, and it's in the habitable zone, all that means is that there can be liquid water. It doesn't mean that there is. So for the Earth, for example, because if you are in a zone where there can be liquid water, usually when the planets form, all of that water is in the form of gas instead of ice, right? And so when a planet like the Earth forms, that water is not going to come on it naturally. You need something to bring it. So for Earth, it was what we call the late heavy bombardment. So there were a bunch of comets and asteroids and stuff like that bombarded the planet after its formation, and that brought a lot of ice and a lot of water that was then on the planet and could make our atmosphere and our oceans, etc., etc., etc. For these planets, we don't know if that's happened, right? So we don't actually know if they have water most of the time. There are certain techniques that can show you that, but if an article just says, a planet in the habitable zone, doesn't mean it does have water. And then even if it does have water, you don't know if it does have life, because you usually need very special techniques to detect certain signatures of life. So for example, the ozone in our atmosphere wouldn't be here if it wasn't for life on Earth. So if you were able to detect that amount of oxygen in a planet, you could say, oh, there's probably something to it. But then even if you can't do that, you don't know what kind of life you're looking at, even if you could do that. And I don't think it's been done yet. You don't know what kind of life you're looking at. It might just be bacteria. For most of the Earth's history, the life that's been on it was very simple bacteria. They're very good at doing their thing and reproducing and not dying and all of that. They're perfect. Intelligent life is very complex and very prone to dying. So yeah,
Okay.
be mindful. It doesn't mean it's not interesting. It is.
Yeah.
If anything, it tells you that our planet is not unique, which a few decades ago people thought, oh, we're so special. We ain't. We're not that special. Like, let's just put it out there. And it's a good thing to remind people we're not that special. But it doesn't mean we've found aliens.
So I'm only going to dumb the conversation down for these next two questions, and then we'll get back to that super sciencey stuff.
Cool.
Do you subscribe to intelligent life out there in the universe? I'm going to use the term aliens because that's just what people use.
I don't really think about it that much, because in my mind, even if there was, so here's the thing, there's like 100 billion galaxies and billions of stars in each galaxy, so maybe. But two things. One, the chance that it's just like us and we could even remotely communicate, even if we were next to each other, seems pretty freaking small to me. And secondly, because of the speed of light being the limit of how fast information can travel in the universe, we could never talk to these people. So in my mind, it's one of these things that doesn't matter, because it will have no consequence on how we live our life. Like, I understand that for people, it will have a consequence in the sense that, like, oh, we're not alone and there's other people in the universe. But even if we find evidence of that, we're probably not going to be talking to these people. We're probably not going to be interacting. Right. And so it isn't. Yeah.
That's a good way to put it, for sure. And the second is, it's like basically Star Wars. Do you think any time in the future, whether that's like the future of human life, like thousands of years, whatever, that intergalactic travel could somehow be a possibility?
So intergalactic is in within the galaxy?
Sure, we'll go with that.
Maybe. So I don't think it would be impossible in the realm of possibilities, but not on a human life scale. So for example, the human race could conceivably explore the galaxy as a race, but you won't live long enough to go from like one end to the other. The nearest planetary, star system that we know is 4 light years away. So even if you could move at the speed of light, it would take you 4 years to get there. And moving at the speed that our rockets move now, you wouldn't make it. So as a race, maybe, especially if we can mine asteroids and make our own stuff and find our own stuff on the way. But Star Wars as it is, Star Wars is Star Wars because it has faster than light travel. Star Trek is Star Trek because it has faster than light travel. That's how all of these like space fantasy worlds can exist in the interesting way that they do, is because they have faster than light travel. And it's just not really possible in the realm of physics. So it could exist, but not the way that we think of it, because the big assumption is faster than light travel.
Sorry, everybody, but you heard it here.
Sorry, it could still be really interesting. I mean, if we made a giant rocket ship that could like self-sustain and everything, that would still be bloody awesome. Can you imagine that? And then being the generation that discovers a star, and like your grandparents will tell you about that star that you're heading towards, and then your generation that finds it, and it's really exciting, and all of that. Like, it could still be very exciting, but that's the kind of sci-fi that I've not read yet. Like, I've not read sci-fi like that.
Right. What are some particular things that maybe like you've read that people are researching, that like, you know, your colleagues, like, what are some things being done right now that really excite you about, you know, the universe and things that are being done?
Oh, that's a really good question. it's a difficult question to answer in a relatable way because I'm a nerd, and so I'm like, I get sucked into rabbit holes of like statistics and machine learning and techniques like that are not necessarily accessible. But science was, well, kilonovae are really cool, which is the main topic of my project. There's also all of it, just in general, what we call transient astronomy. So a transient is an object in the sky that only lasts a small amount of time. So for example, a supernova goes bright and then within a few weeks it fades. A kilonova fades within a few days. But there's loads and loads and loads and loads of types of transients. And we're discovering more and more every year. So there's new things and we give them names that are crazy because we don't know what they are. So for example, this type of transient called fast blue transients. Not sure exactly how they come about, but they come quickly, they disappear quickly, and they're very blue. So they're called fast blue transients. There's also calcium-rich transients. Again, they're similar to other things, but different and in different locations. Not sure what's going on there, but it's full of calcium, so we'll call it calcium-rich. And it's a very astronomer observer thing to be like, I observe a thing and I will give it a name. Doesn't matter what's behind it because I don't know yet. And then we'll just try and sort out the classification later, which we never do. That's why classifications in astronomy are an absolute mess. But this is happening at the moment. Transient astronomy is going really big because we have telescopes that just scan the sky, just without a specific target. They just scan the sky to look for these new things, these new quote-unquote stars. And we've got a new telescope that's going to come online soon called the LSST, the Large Synoptic Survey Telescope, which is going to have a giant field of view and can scan the sky like every 3 days, the entire sky. And you're going to find so many transients with that. You're going to find so many of these new things. And it's going to be able to tell us about what these like little stellar explosions are. Like, are these stellar explosions? Is the star dead? Has it just lost a bit of its outer envelope? Is it still there? Is it going to do it again? There's things like fast radio bursts, which like so many people are wondering what they are. Like, that's a real exciting area of astronomy. It's what it says on the tin. It's a radio burst and it's fast. That's, it happens quickly. Mm-hmm. And so people wonder if it's comes from black holes or come from neutron stars that quake. There was a paper last week about quark novae. So it would be a really dense object that turns into quarks instead of it's even smaller than neutrons. Quarks are what makes neutrons and protons. Okay, so you're even going further. You're going even denser than a neutron star. And they were wondering if that could be what fast radio bursts are about. And so you get all of these crazy theories to try and explain it. And so that's what's going on at the moment. That's really exciting. Interesting.
Okay. Curious about galaxies. So in my limited research of what I was trying to, come up with to find some cool things about the universe that I could ask you about, one of the things that came up was cannibalistic galaxies.
Yes.
So when we talk about, is that like a galaxy crashing into another galaxy? Am I on the right
path? So I guess that would be the merger of galaxies, which happens. It's something we even have pictures of that, actually. And the Milky Way is doing it.
Oh,
it is. There's a bridge between, is it the small Magellanic Cloud or the large Magellanic Cloud? But there's like a stream of gas between the Milky Way and some of its nearby galaxies because it's bigger than them. And so it's the same concept of the gravitational well, right. Of, it warps space-time, it creates a well, and if you get too close to the well, you fall in, right? And so it's the same concept, just on the scale of a giant galaxy instead of a tiny neutron star, but same idea. And so these stars will get absorbed by the Milky Way eventually. Andromeda, the Andromeda galaxy, is, if you're a Mac user, then you'll know because it's the background of a lot of Macs, of a lot of MacBooks. It's that galaxy. That's on its way to merging with the Milky Way in a few billion years.
Okay, so we got time.
Yeah, we've got plenty of time. And the thing is, when we think about merger of galaxies, like I said before, space is really empty. There's a lot of room between the stars, and so the stars are not going to collide That's not really going to happen. What's going to happen, though, is that the gas in the galaxy is going to collide, in a sense, and it's going to create new stars. So it's going to compress the gas, and it's going to create a new generation of stars.
Interesting. Okay. And more things to study. There you go.
Yeah.
Dark matter is another thing that comes up a lot.
Mm-hmm.
Can you explain that a little bit? I'm not sure. I know space is, again, one of those things that's so big. I don't know exactly what falls under all the purviews of what people are studying. But like, can you explain it a little bit, and how I'm not to use a bad pun, but like how it matters?
So dark matter really isn't my area, but I know the basic gist of it. It's more like physics and cosmology, but I've got friends that study it, so there's a few things. People sometimes get confused between dark matter and dark energy. They're different things. So the universe, in its energy budget, right, about 5% of that energy, because mass and energy are like equivalent, E equals mc squared, Einstein, all of that. We're all somewhat familiar with that in the general culture. So matter, energy, similar. So 5% of this energy budget is in the form of ordinary matter. So stars, galaxies, us, all of that stuff. About 25% is dark matter. And we know dark matter is a thing because of the way that stars revolve around galaxies. So stars go around their galaxy, the center of that galaxy, and you can see at what speed they're going. And if you look at that speed and you try to simulate what would happen if the only matter there was the matter you see, then it doesn't match. So we know there is extra matter there that makes stars go around the way they do. So that's one thing. And people argue different things that I don't understand, because it's physics. Like, they've got these special particles and everything. So some people used to think that it was maybe stars that you couldn't see. Some people tried to shoehorn a different type of gravity called MOND, M-O-N-D. Some people still think it's a thing. I don't really know. I don't have any allegiance to any theory, because I don't understand it enough. And there's lots of elementary particles. People used to think maybe neutrinos were the dark matter, but it's not. Neutrinos are really, really light particles that move pretty much at the speed of light, but they don't interact with you. The sun creates a lot of neutrinos, and they go straight through Earth. Like every second, what is it, 7 billion neutrinos go through your thumbnail, something like that. Pretty insane.
Okay.
But they're too light to be the dark matter we know. So dark matter is a thing, and then dark energy is a thing. About 70% of the energy that of the energy budget of the universe, and that comes about from just general relativity, which is the general theory of gravity and how the universe works. And I wouldn't say it's a mathematical trick, because it works, it makes us understand the way the universe works, but we don't really know where that energy comes from. And I don't really know what theories are about it, because that's really deep into like cosmology, maths, like really theoretical stuff that is really far removed from my side of astronomy, which is more observer based. Like, I see a star, let me study it. Like, this stuff for me is it's like pure maths to me. But yeah, I've got a few colleagues that work on dark matter and stuff like that. And the type of maths they do, it's not the same. It's not the same maths I do. Like the other day, it was so funny. They were showing us a paper that they were interested in. We have a journal club like every week, and we show a paper that we found interesting. And there was an equation, and there was a square in it, just a square. Okay. And I was like, is that a typeset error, or is that a mathematical symbol, and we're like, oh yeah, no, it's just an operator. Like you get to the type of maths where you don't have numbers anymore. You've got letters, but you also have shapes. It's just straight up shapes. Like we ran out of letters, you've got shapes in it. You've got triangles, you've got squares, and they mean different things, and I don't know what they mean. It's really crazy. It's really cool.
Hieroglyphics going on.
Yeah. You look at this, you're like, I don't know what happened.
Okay, so I'm curious, and we're going to circle back on when we were talking about gravity. My other question is about the universe, and I've read that it's infinite and it's constantly expanding.
Yes.
Does that that's too big of a question. I was going to ask, does that affect
it's such a hard question. I've had so many drunk arguments with people telling me that it's not possible and blah blah blah.
But
it's
and
very
how
difficult.
do we know it is? How do we know that it's constantly expanding, and what does that mean?
So the universe is finite but unbounded, first of all. So finite means there's only so many stars and so many galaxies, which technically you could count and get to the end, right? We know that because of some thought experiments done in the 20th century. It's called Olbert's paradox. I can't remember how that's spelled. That's like first year of astronomy. That was a long time ago. First year at uni, I mean. And basically what it says is if the universe was infinite in time, so was always the way that it was, which is what people used to think in the 19th century, and if it was infinite in size, then in any direction that we look at in the night sky, we should see a star, because the light from that star has had infinite time to reach us. So it should reach us, right? And so if that was true, then the night sky would not be dark. Since the night sky is dark, we know that it can't be infinite, because otherwise it would be as bright as a star. So that's the thing for the finite universe. Now we know that it's expanding because we can see that. And it's a phenomenon that's called the Doppler Shift. So, and you can, there is an intuition for it. So if you've got an ambulance that's coming towards you and then goes past you and going away from you, the sound from the siren changes, right? As it comes towards you, it gets more high pitch. And then as it moves away from you, it's low pitch. And that's for sound, but for light, the same thing happens, except we don't have high pitch and low pitch. We have blue and we have red. So if something comes towards you really fast, it will look bluer. And if something moves away from you really fast, it will look redder. And that's something that observers, astronomers deal with all the time. Like you take an observation from a star that's really far away or a galaxy that's really far away, you're going to have to account for it, because it's not just a phenomenon that happens, it's a phenomenon that is very visible and that actually impacts your observations. So we know things are moving away from us. And we can actually measure at what speed they're moving away from us, and all of that. And so what we've noticed is that the further away something is, the faster it's moving away from us. And that's the expansion of the universe. And we know the expansion of the universe is accelerating because of that curve, and because we've been able to measure things that are really far away from Earth, because supernovae are really bright. That's one of the pros we have. So they're so bright that you can see them in other galaxies that are really, really, really far away. So you observe the supernova, you know what kind of color, what kind of brightness it should have, and you can deduce how fast it's moving away from you. And with that, you can build what we call the Hubble diagram, which I encourage people to Google. It's not a difficult concept there's no maths. It's not a difficult concept to grasp, and there's a good Wikipedia page on it. And that's the expansion of the universe that we measure.
Why is science, why is communicating all this stuff really important to you? Because I know when I found you on Twitter, you were talking about how you love doing outreach and explaining this. Why is that something that you enjoy, that you're passionate about?
So on a personal level, I really love doing that because it helps me rekindle my love of science. Sometimes it's easy to get bogged down in the nitty gritty of my code is not working or this is not working. Like being a scientist, in essence, is having problems all day, every day, and trying to solve them. And so doing outreach and talking about, the essence of what's interesting about science, really helps you keep that big picture in mind. But I also think it's really important for people to be interested in science, just in general, because scientific inquiry and the way that you have to use critical thinking and the way that you have to learn how to read graphs and all of that basic stuff is actually very important, especially in the day and age that we live in, where there is so much information out there that people have to filter through. And be able to use their critical mind to distinguish between what is true and what is false, to be able to distinguish between, some media outlets that are trying to make graphs that make things look the way that they're not. We've seen that with Fox News, that they mess with graphs and everything. But you need a basis for that. You can't just throw a graph at people and be like, here's how you learn to read a graph. That's boring. It's boring. But if there's some really cool and awesome science, that, and astronomy, I think, is one of them, then it gives people a playground to learn all of these skills and to also learn really cool things about the universe and our place in the universe. And so I think it's really important for all of these reasons.
Yeah, absolutely. Before I let you go, I do want to ask, because I don't have any kids, but I have two young sisters that are 6 and 5. And I'm just, I grew up in a small town. I reference that a lot on the podcast here in Canada, but the opportunity for them, like, I want the future to be, like whatever they want to do. If they want to be an astrophysicist, I want to do that. I know the issue comes up, and I don't understand a lot about all the nuances, but like the women in science and women in tech is a big issue right now in conversation. I'm just curious, what can we do as a society to help, open those doors and then keep them open for young people, young women, young people of color from different sexual background, whatever. How do we open the door for them? How can we help as, regular everyday people push this forward? So if they want to go to space, they can do that, no problem, as long as they work hard.
That's a really good question. So there are two main things. First of all, educate yourself on unconscious biases. Research unconscious bias and what they are and how you can become more aware of them and combat them. That's a really good thing to do. About the women in STEM in particular, and especially for young kids, gender roles. Be aware of gender roles and try not to put people in a box. And I would say that for both men and women, because men suffer from gender roles just as much as women, in my opinion. Toxic masculinity is something that men suffer from just as much as women. And I would encourage people to educate themselves on that, because that's where you realize how you might have been treating your daughter different from your son. There's an excellent book called The Gendered Brain, which I highly recommend, written by Gina Repo. I'm sorry, I'm reading it because I see it on my shelf, which is excellent for that. Because a lot of people think, oh, men and women are just as good, but they're just different. But oftentimes they're not. What's different is the gender roles and your expectations of men and women. So, for example, women are so much more mature, although, oftentimes it's just because they are punished for the same things that boys are allowed to do. And so they have to grow up in a world where they have to be more mature. They are held accountable for the bad mood of men, and they have to deal with it and police themselves. Similarly, men are not allowed to show emotion just as much, or are made fun of for it, or are not given the same amount of support. And that's true in childhood as well. And that's a problem. So I think that educating yourself on gender roles and starting early, with kids, just not putting them in a box, getting the girl her Legos if she fucking wants them, and educating yourself on that. It's so important, because gender roles get into kids' heads very early. Very, very early, and not just from the parents, from society. And so you have to work extra hard as a parent to combat that, because it's on television, it's in adverts, it's in books, it's everywhere, and it's problematic. We see it has an effect, not just in science, but in society. And for example, in science, even the women that are in science that have made it, we've had a very interesting article come up recently in Nature. So with the pandemic, everyone's at home, right?
Mm-hmm.
So you've got to work from home, you've got to do childcare from home. Men's output in terms of number of papers has gone up by 50%, roughly, and women's has gone down by 50%, roughly. Mm. Because women are carrying more of the burden of childcare and household chores. So, and that's not something that scientists themselves can really do anything about on a systemic level, because that's a problem with society. And so I would encourage parents to educate themselves about what gender roles they have evolved in and they might be imposing on their children without even knowing.
Right. Well, listen, I really appreciate you joining me and giving me some time in your morning over in New Zealand. If people want to get some more information, I know your Twitter is one of the most fabulous Twitters, and I love following.
Oh my God, thank you.
Because it's just like having the conversation with all these, you just post all these interesting stuff. So I love following along. Where can people find you? Do you have a website, Instagram, Facebook, YouTube, podcast?
Oh, I don't have a podcast, bless me. I've got a website. So my website is hfstevance.com. So just H for Heloise, F for Fanny, because that's my proper name, and Stevance is my last name. Just all of that together.com, and that's my website.
Perfect. And we'll make sure we include a link and everything, and website and do your Twitter. Really appreciate it. Like I said, I was so excited to talk to you, and it met every expectation and more. So I really appreciate it.
Thank you so much, Ryan. It was so much fun. You had amazing questions.
Oh, thank you. All right. Take care.
Okay. Bye.
Bye.
You take the red pill, you stay in Wonderland, and I show you how deep the rabbit